Okay. Well, good morning. Pretty small crew this morning, but that's not unexpected. I think 8 a.m. on Monday morning is probably the worst, or uh, uh, the toughest time uh, during the whole week. Um, but this is good. We'll have having this session this way. No one should have any conflicts or anything, so we'll have more flexibility too. Um, so let's see. Sounds like folks have had a nice weekend, and um, yeah, hopefully, having to be stuck inside, it's almost like if the weather is not nice, it's kind of like another reason. So, it's all good. So, today we're going to talk about gravity. Um, and before we talk about that, I wanted to mention one logistical issue, and that's I posted a quiz uh, on the homework system. So you have a couple 3 days in which to do it. It's very similar to what we did last time around for kinematics and projectile motion, except it's actually um, more conceptual. So I think it should be. There's more questions too for the same amount of time. So it should be. I think you should be able to do better because any one question, if you get it wrong, it's smaller fraction of the whole quiz. Um, and we'll see how folks do on that. I think you'll find it's not too bad. Um, but I also, by having it be more questions and having it sort of lower stakes per question, hopefully that sort of eases the all or none nature of the online quiz. And then in addition to that, there is one problem that's posted in Blackboard. Now, I was looking at the settings and stuff. Turns out there's not a good way to have a time window. So that's basically a take-home problem. And you have a few days in which to do that too. I made them both due on Wednesday. Um, so, like I think I've expressed to you before, it seems like there's just not really great ways to do assessment online. Um, so we're going to err on the side of making it more flexible and basically in your favor because I don't want people to be stressed out by the assessment aspects. Um, but I do want you to know what you're expected to know, and I want you to so you can approach this in different ways, right? You have a lot of access to resources that we wouldn't have normally during assessments, and I think some of those that you should take advantage of. If you have your notes and everything in front of you, I think that's fine. But be aware if you take this as an opportunity to like, well, what does the internet have to say about our assessments? Don't do that because I think it's only gonna hurt you in the long term. Because then once we get back to school in person and you're staring at a PH 2021 exam and you're like, oh man, I don't have these resources that I had now, it's really going to be tough. So I think you should take this as an opportunity to push yourselves and test yourselves so that you're better prepared for subsequent courses. That would be my advice to you. And just be rest assured, uh, I'm not going to let your grades suffer as a consequence of the online environment. So we'll make sure that things are okay on that front. But please push yourselves and don't, make this an effort, an exercise in using Google to solve quiz problems. Cool. So let me just put a reminder on this whiteboard about this. Um, so there's one. Uh, well, let me put it to you this way. So there's one part that's in the homework system and one part that's on Blackboard. And even put together, I gave folks a lot of time. Looking at how long it took us to do the quiz last time, you're going to have more time. So I think total this is these two pieces each. You have well, yeah, like I said, this will be I think this is 25 minutes. And then this one you have as much time as you want. And then this will be due, Wednesday. And then the other thing, of course, that's due is the homework, but that'll be due on Thursday. And this will be on the current chapter, so we need to talk about that stuff today. Okay, so that's just sort of administrative issues that I wanted to mention. Does anybody have any questions about that? Just please let me know if you have any concerns, or if you're working on that and you run into some technical issues or whatever. Like I said, I want this to kind of err in your favor, so I think you'll find that it's not that not so bad. Okay. Well, if you have any concerns, let me know. You can shoot me an email, or let me know in Teams. All right. So back to physics. What have we been doing? Um, so most recently, we were talking about centripetal acceleration, circular motion. That was sort of the tail end of chapter 5. And it turns out that that was a transition to get us talking about gravity, which is chapter 6. Now, this is a super fun topic because this is it's a very sort of juicy physics topic. And it's cool because it lets us talk about things like planets and satellites and space travel. And it's just an in for a lot of fun applications. Um, so, okay, let me see. Let me get our. So, and this is the next chapter. We're coming from centripetal acceleration. We've been talking about forces, Newton's laws, and now one of the ways in which gravity is a lot different than what we've talked about is everything that we've talked about so far with regards to forces has been things that are in contact. So you have, you're pushing on one object and that object pushes on something else, or, you know, uh, you have one object that's connected by another object. Everything, all these situations, things are touching. Things are touching. And gravity is not like that. Gravity is not, there's no contact involved. Which is an interesting contrast. And at first it might seem like, well, how does that work? And we're going to talk about today. So it's pretty amazing, but gravity is also, let's see here. Whoops, sorry. Gravity is also a product of Newton, or the type of formulation of this that we're going to talk about today. So we can thank Newton for this as well, which is pretty amazing. He was definitely a really prodigious scientist. And this is the way that the definition for Newton's gravity, this universal gravitation, is defined in your book. And I will just read it to you, and then we can kind of talk through it, and then we'll talk about it in more mathematical terms. So, the law of universal gravitation. Every particle in the universe attracts every other particle with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them. And the force acts along the line joining the particles. So, a couple things. It depends on the mass, and it's proportional to the masses and inversely proportional to the square of the distance. So what this looks like in mathematical terms, if we're talking about just the size, the force of gravity, it's proportional to the masses between two bodies. And here, let me give you a cartoon. Okay. So it's attracting. So those, I've drawn those arrows pointing towards each other. And it's proportional to the masses, inversely proportional to the square of the distance between them. And the force acts along a line joining the masses. So this is sort of the functional dependence. And the thing that we've omitted so far is the proportionality constant. There's a constant that we call big G, the gravitational constant, that tells you how strong this force of gravity is. A couple side things. This is an inverse square law, is another term for this. And you can see why that's the case because it depends like 1 over r squared. And this is something that appears in other places in physics. You will see this again. In particular, with respect to electrostatic forces. So you'll see this again. In the next quarter. It's a different situation that has to do with electric charges and stuff, but it has the exact same behavior. So, have you guys seen this before? You guys learned about like this? Okay, high school. Okay. Okay. So maybe this is not like a super new situation, and that's okay. Okay. Um, so I've been thinking about, I guess I'll say, we can get a lot more sophisticated with this, and I think we'll try that in lab. And uh, so, yeah, a lot of the things that the sort of problems and stuff that you can come up with for this are analytical, right? But in practice, a lot of the types of problems that you'd want to solve are they quickly become you can't solve them analytically. So in lab, we're going to try and do some numerical stuff with gravity. It's a little bit of an adventure because we haven't approached it that way before, but the fact that like you guys have all seen this law of gravity before, I'd take as, an incentive for us to try and push on some things that we haven't seen. Because one of the things that kind of a goal for us is for folks to see new stuff, which is kind of a challenge with a class like this because there's going to be folks who haven't seen this before and they need to know, need to know the basics before we can proceed. But for folks who have seen it a little bit, I want to show you something new. So we'll try. Stay tuned. We're going to go through some basics today, but in lab we'll look at stuff that's a little more out there. Okay. So you can see how this, just a couple notes about how this depends. So it's proportional to the mass. So, if you were to say double m1, then the force of gravity, you'd get 2 times the force of gravity. It's proportional to 1 over r squared, though. So if you were to say double r, then that would mean you pick up a factor of 1/4 times the force. So you see kind of the functional behavior of this. Another thing about this is that G is very, very weak. So we call it big G, but this is a tiny number. So G, wow, I can't draw G. G is 6.67 times 10 to the minus 11. And the units for this are newtons meters squared per kilogram squared. And we can verify that this makes sense because notice we're multiplying by kilograms. We're multiplying it by kilograms times kilograms over meters squared. And you can see that would cancel and we'd be left with just newtons, which is what we want because it's a force. So that's why it has that combination of units, because we want this to give us a force. Okay, let's see. One other detail. So these are just sort of little tidbits about this. And this is really helpful in terms of being able to solve problems. And that is the fact that we can treat a spherical mass distribution. So we're going to be talking about things like planets. And it so happens that things like that are spherical behave just like as if they were points with all the mass at the center. And this greatly simplifies solving problems. And we're not going to go into deriving this, but you can show, and actually they show in your textbook this piece of information, this fact. And you can look in Appendix D. How you would show this basically is, you imagine like you have some spherical, rather than having just a point, between 2 points like I drew up there, we would have to sum over all the contributions of like this distribution. In other words, you would sum over some density for that, and the distance between each element in that distribution sum over the volume, etc., and it becomes an integral. But since uh, it's a three-dimensional integral, it's a little bit complicated. And I know that not everybody has messed with that in their calc classes yet, so we're not going to talk about that in class. But if you're curious, if you look in Appendix D, it tells you how to do that. Um, it's basically a three-dimensional integral. Okay. So, questions so far? Ah, yeah. How is big G different from little g? We'll talk about deriving one from the other in a second. So that's coming up. The short story is big G is this gravitational constant. I'll put a note on here. So big G to be distinguished from little g, which is this is the acceleration due to gravity at the surface of the Earth or some other body. So this would be little g, and this is, big G. But yeah, they're related. We'll talk about that in a second. Other questions? That's a good question. That connects what we have been talking about in class to what we're talking about now and kind of where we're headed. Okay, so that's basically the first section in chapter 6. Let me be a little more technical or a little more correct in our definition. So the first way that I describe this is just telling us the magnitude, but it's not telling us exactly where it's pointing. And we can put this in terms of our vector notation. So this is done in the next section. And we'll spend a second talking about this because this will be relevant to what we're going to do in lab. So basically, if we're a little more detail-oriented, if we want to find the gravitational force between two masses, I'm calling them M1 and M2, it's going to depend on the vector distance between them. And it's going to point. So I've denoted that by R21. So that would be the vector that connects 2 to 1. The arrow over the top of it tells you that it's a vector. Now, R21 hat, that is the unit vector. So this is basically R21. You can think of this as R21 divided by the magnitude of R21, because recall that a unit vector is a vector of length 1 that points in some direction. Now, we're familiar with, I hat, j hat, k hat. Those were the unit vectors that we were using to label the x, y, and z directions. So these would be vectors that have length 1 that point along x and y and z. Well, R21 here is the unit vector that points between 2 and 1. And so I just wanted to take a second and be a little more explicit about this. So this would be, think of this as the force of gravity on 1 due to 2. So what does that look like? Well, it's big G. It depends on the product of the masses. It depends on this R21 squared. And it turns out this is negative because it's an attractive force. So the force on 1 due to 2, 1 is going to be attracted to it. So if we draw in the force vector, it would point from 1 to 2. And the direction, how we indicate the direction, is to say this is R21 hat. Okay, so the different pieces that we have going on, let me just walk through the whole thing. So this is the force of gravity on 1 due to 2. So on mass 1 due to this mass 2. How does it depend? Well, it depends on its size is gmm over r squared. It's pointing along the unit vector r21, but since it's pointed from 1 to 2, it'll be negative. So this is the more correct definition. And why this is important is because this allows you to actually ground this law in a coordinate system. So if you want to do anything quantitative in a coordinate system, you need to have the actual vectors, unit vectors, and stuff that this to anchor it in the coordinate system, and that's how you do it. So you can look in section 5.2, or sorry, 6.2 about this. But we're going to talk more about the more correct definition in lab. So kind of stay tuned for that. We'll talk about it tomorrow or Friday, depending on what lab section you're in. Okay. The one other sort of piece of information that you need with regards to this more correct vector formulation. So yeah, you can think of this as basically the vector formulation of the law of gravity. So the one other piece of information that's in that section is the fact that if you have more than one mass, so this is just the version where it's like, oh, we have, these two masses. But suppose in addition to mass 2, you have another mass 3, you have a mass 4, maybe you have, you have other masses. Well, it turns out if you want to find the total force of gravity on 1, you can add these together. So you would add the force due to 2 plus the force due to 3, etc. i.e., if you add them up, you can find the total force due to gravity on something. And it's the same sort of addition of vectors that we've talked about with regards to things like, in different contexts, like imagine you have forces of tension. Suppose, like you have different uh, chords attached to an object. It's the same kind of math. So, and except the force now is given by this law of gravitation, the size of it. So, and that's kind of cool because you can solve for the same kinds of things. You sum the forces, i.e., you add up the contributions from different masses like this. If you know the force, then you can find, if you know the net force, you can find the acceleration from Newton's second law. Okay, so had you guys seen this described as a vector before, or just the magnitude? I suspect you probably only talked about the magnitude. Yeah, okay. And that's okay. For the most part, we've only talked about the we'll only make use of the magnitude too, but you need to be aware of that. And it'll be super useful for you to have seen something like that, I think, because when you talk about electrostatics, you often do problems where you add charges. And if you see that with gravity, then it'll be more familiar when you encounter it with electrostatics. Okay. So that's kind of the more detailed. We'll deal with that more in lab, but file that away for the moment. The next thing that I want to talk about is connecting little g and big G, like to your question. So, Krishna, how do we do that? Well, recall that if we wanted to find the force of gravity, like for an object that's, this, what do? We just multiply g by the object's mass. So if this was a block of mass m or whatever, i.e. mg. Well, what we're saying here is that this is the same thing as big G, the mass of the Earth, times our mass of our block, over the radius of the Earth squared. So the two different ways of thinking about this is we've been talking so far about like an object that's sitting on a table or something like that. In terms of this universal law of gravitation, is you have an object that's sitting on essentially on the surface of the Earth, and where this is the radius of the Earth, and you need to know the mass of the Earth and the mass of that object. These are the same. It'll give us the same number. So you can see how both sides depends on m, the mass of the object. This gives us a definition for little g in terms of big G. It's g times the mass of the Earth over the radius of the Earth squared. Okay. And you can estimate this. So, and see that this makes sense. I told you before, so big G is 6.67 times 10 to the minus 11. The mass of the Earth is 5.98 times 10 to the 24 kilograms. And the radius of the Earth is 6.38 times 10 to the 6th meters. And this is quantity squared. So notice, let's just do like a rough calculation here. This is approximately 6 times 10 to the minus 11 times 6 times 10 to the 24. So in other words, the numerator here is about 6 times 6 times 10 to the 13. The denominator, we have 6 times 10 to the 6th, quantity squared. So that would be 6 times 10 to the 6th times 6 times 10 to the 6th. So in other words, it's 6 times 6. What do you do when you have exponents squared? You'd add them together. So this would be 6 times 10 to the 12. And then notice this is basically all the same, except what would this roughly equal? So these would cancel, be 1, essentially, to the power of 13 over the power of 12. So this would be approximately 10. And that is what G is, right? So we know G is 9.8 meters per second squared. So just roughly estimating this, we get the same thing. So that is how you connect little g and big G. And we'll look at example. Actually, we can do that right now. Let me show you an example. With the moon. If I can find it here. Oh, shoot. Whoops. Sorry, one moment. So to exercise this idea, here's a question for you. Let's calculate the acceleration of gravity on the moon. So this will be a little bit different. So the moon's radius is different. It's a lot smaller than the Earth. And its mass is different. But it's the same idea. So we know the force of gravity on the moon is going to be m times g, but now this is, let's call it g moon. And what is that? It's big G, so that's constant for everything, right? The mass of the moon times whatever the mass is that you're talking about over the radius of the moon, quantity squared. So just like we did above, that mass appears on both sides. If we divide a force by a mass, what do you have? You have the acceleration, right? So, and then we can compute this. So we would have 6.67 times 10 to the minus 11. Seven 0.35 times 10 to the 22nd. Yeah, so look at the mass. The mass of the moon is something like 100 times smaller than the mass of the Earth, which is pretty crazy. And then divided by the radius of the moon. Quantity squared. And you find that this will give you 1.6 meters per second squared. So this is G moon. So this would be a really common kind of example question, like in homework and stuff. Find basically the acceleration on other bodies. So on the moon, it's 1.6, and this kind of agrees with our intuition, right? So think of clips that you've seen of like the Apollo missions and whatnot, and you see the astronauts, bouncing around. They can jump really high. That's a reflection of the fact that the acceleration due to gravity on the moon is a lot less. It's only like a sixth of what it is on the Earth. Cool. Um, Questions on that? Questions? Questions? You guys doing okay? Oh, did I mess something up here? Let's see. Oh, I put the wrong number in. Yeah, good call. Not the mass. Yeah, good catch. So you can imagine doing other more complicated problems with this. So, for example, let me show you another example question. Ah. So another, thing to kind of in the same vein to think about is, so far we've been talking about on the surface, and all the stuff that we had done up to this point had been like, well, g is constant, right? Little g is constant. So the other way that you can think about this is like how, if you change how far you are from the center of the Earth, you can see what happens to the effective g, i.e. what happens to little g as a function of r. Um, so that's what this question is asking. How far above the Earth's surface will the acceleration of gravity be half what it is at the surface? And we have, the mass and the radius of the Earth. So in other words, let's take a stab at this one. On the surface of the Earth, we know that g here is 9.8. And now the question is, and that is at the radius of the Earth. Now we want to know, like, how far above the surface of the Earth do you have to get to where g would be, let's call it like g prime or something, would be half of little g. Okay, so we can approach this in the same fashion. We know the force of gravity, size of it anyway, is big G mm over r squared. And we know that that's m times g. Now, instead of g, we're going to be talking about g prime, where g prime is just going to be 1/2 of... Well, here, let me do this. So we'll notice these masses will cancel again. And then g prime, we're looking for what would give us 1/2 of g at the surface. Okay. So in other words, we want to know what r is. So we want to solve for r that would give us this. And notice, and this is sort of a tip or something that I think makes solving these kinds of problems easier, is to make use of the fact that r that we're looking for is going to be the radius of the Earth plus some height. So it says how far above the Earth's surface. So that is definitely like a height as I have drawn it in our picture. But it's easier to just work with r. And then once we know what r is, subtract off the radius of the Earth, and then that'll tell us the height. So let's proceed like that and just solve this for r. Okay, so how would we solve this for r? Well, we could multiply by r squared, divide by this stuff. Let's see what that would look like. So r squared would be 2g mass. Oh, I should say this is the mass of the Earth, right? Divide by little g. We would need to then take a square root. And this would give us the r. And just to have it in front of us, let's put the actual numbers in. So g is 6.67 times 10 to the minus 11. The mass of the Earth is this 5.98 times 10 to the 24. Little g, of course, is 9.8. Take a square root. If we evaluate this, then we find that this r is 9 times 10 to the 6th. So this is the radius where g goes to, let's call it g prime, goes to 1/2 g. Now, if we want to know how far that is above the surface of the Earth, we would make use of this piece of information. So h, I'll just rewrite it here. So the radius is the radius of the Earth plus that h. So if we want h, we would solve for that, and it's just the radius that we found minus the radius of the Earth is going to tell us h. So we would take 9 times 10 to the 6th minus the radius of the Earth, 6.38 times 10 to the 6th. You subtract those, and you find that the height would be 2.6 times 10 to the 6th meters. So that's the height at which the acceleration due to gravity would be 1/2 the acceleration at the surface. Questions? So that's another, sort of common example of the types of problems that we could solve in terms of, looking at the comparison between big G and little g. And this is basically section 6.3. I would encourage you, let's see. Oh, did I make a mistake? So our factor of 2 is in here, actually. It's right here. So it is 9.8 over 2. So yeah, like I said, this is basically up to section 6.3. So I would encourage you to read chapter 6. Uh, this section 6.3, we're not going to talk about all the examples that are in there, but there's some really cool examples like it's got some really neat what if you're on a mountain? How does this change? They look at an example of like, what if you're on Mount Everest? How is little g affected? Or they look at in that chapter as well, like what effect does the Earth's rotation have? So I don't know if you are aware, but like um, all satellites and stuff are launched from locations that are pretty close to the equator of the Earth, and that has to do with the fact that the rotation of the Earth is helpful. It lowers the effective g that you need to get off the surface. So um, that's why, and they explain to you in section 6.3. They give you an example of that. So let's see. Yeah. Uh, yeah. I mean, there's probably different ways that you can think about this. This is just one way of talking about it. These examples in section 6.3 will be kind of in the same vein. I would encourage you to look at that and read the rest of chapter 6. Um, let me put it like this. And we'll talk next time about connecting this with what we talked about with centripetal acceleration. And we're going to use the force of gravity as the force that's providing the centripetal acceleration. So that's where we're headed. Do you guys have other questions? Any other questions? So we'll talk about building on this in lab as well. If I have you with, I will either see you tomorrow in lab or we'll see you uh, Wednesday with more lecture. So I'm going to try and be a little better about your time. I don't want to bleed over into your next course obligation if you have a class, quote unquote, at 9. Um, so next time we'll look at the centripetal acceleration. Okay, well, if there aren't any questions, I'm going to end the stream, but shoot me an email or contact me on Teams and we can chat if there's anything. Okay. Well, have an excellent Monday and we will see you soon.